Hi, hello everyone. This is your educator, your tutor, your friend Sanjay Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. Do watch this session. If you like it, do press the like button, share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Okay? You can go visit our website www.we-learning.in. These classes you will be getting there. Along with that, you will be getting lecture notes for each and every session. Okay, you can go check it out. Now, without any delay, let's get started with today's session. We were doing electrostatic potential and capacitance, and this is lecture number 10. In this lecture, we are going to talk about parallel plate capacitors. In the last lecture, if you remember, we started capacitors. We did an introductory session for that. I told you why capacitors are used, right? What are capacitors? We spoke about spherical capacitors. Why don't we use spherical capacitors, right? After a lot of advancement, we came up with a solution that is parallel plate capacitors. So let's study this. So what are parallel plate capacitors? From the name only you can understand. Two plates kept parallelly. Something you can understand, right? So now exactly that is correct. Two plates kept parallelly at a separation, at some separation. Okay, two charged plates. Now these are conducting plates. These are conducting plates. This is having some charge, let's say Q. The same charge with opposite nature. Okay, equal and opposite charge will be on the plate which is in front of it. Fine, parallelly, which is kept parallelly to it, and both will be, let's say, are at a separation D. Fine. The area of the plate is A. Now here, the area of this plate should be same as the area of this plate. Okay. The charge on both the plates should be equal inside. The charge inside both the plates should be equal. The inner surface I'm talking about. Fine. And there should be some separation. So this is a parallel plate capacitor. Now, how it is better from that? From the spherical capacitors? Just understand. This is plus, this is minus. If I make electric field lines, they will be like this. Correct? Electric field lines are bounded. The energy is bounded here. The very first benefit there, why didn't we use spherical capacitor? Because the energy was not bounded. It was scattered. It went till infinity. Correct? The electric field lines were there till infinity. So now here, energy is bounded. If you remember, I told about capacitors that why do we use capacitors? Capacitors are something which hold a lot of electrical energy, right? And there are some appliances which need a lot of energy in the starting to start that all at once. And then later on they can be running with a normal steady current, correct? So now this capacitor, if you see, it is, since the electric field lines are bounded, the energy is bounded. Whenever it will be necessary, it can give the energy all at once. Fine. Second thing is, the capacitance is more. The capacitance is more. How the capacitance is more? For your understanding, see, C is equal to Q by V. This is the formula what we studied last time. C is equal to Q by V. Now, this is basically delta V. This is basically delta V, potential difference between the plates. There also delta V only was there. But why didn't we write delta V? Because if you see this spherical capacitor, the electric field line, suppose this is positive, the electric field lines are going till infinity, correct? Now we know that electric field lines go from positive and terminate at negative. We can assume that there is one more spherical surface at infinity, which is having a negative charge. See, now these radial electric field lines are justifiable, right? They are coming out from positive and they are getting in, they are ending at negative, right? So this surface is at infinity. So now if I take the potential difference, this is V infinity, this is V. V minus V infinity. V infinity is 0, that is V. So there it was Q by V. Clear? Here what did we do? We brought this plate closer. So now if I bring the same plate closer, what will happen? See here. In spherical capacitor also we can actually bind the energy. See here. We can make the energy bounded. Now if I make this, if I bring this surface closer, now see, the electric field lines are bounded, correct? But still we don't use spherical capacitor because of certain reasons. So now here, the same thing. This negative plate was at infinity for spherical capacitor. Now I brought it closer. Since I brought it closer, now the electric field lines are bounded. Okay. So this delta V, I hope you understand, it is the potential difference between both the plates. Now see, because of this negative charge, the net potential will be reduced. If I remove this negative charge, potential due to this positive charge will be high. Some potential will be there. If I bring a negative charge, then a negative potential also came. So the sum of the potential will be less, right? So if the potential decreased, if the potential difference decreased, C will increase, because of which capacitance is increased. Capacitance is more than that of spherical capacitor. Fine. Now, other thing, this area and D, the relation between A and D should be very less than A. This separation should be very small. The more small the separation is, the more will be the capacitance. Okay, I told already, capacitance does not depend on charge and potential. Charge and potential can be depending on capacitance, right? According to the capacitance, how much ever charge is there, that much potential will come, correct? But capacitance does not depend on both. Capacitance depend on the shape, size, medium, and all those things. Once we'll get the equation for the capacitance of this, you will understand. In spherical, anyways, we saw 4 pi epsilon naught r, correct? Now here, it depends on this separation. It depends on the area also. Okay, and this D should be very less than A. Why? Otherwise, these electric field lines will not be straight. If you remember the first chapter, electric field lines from an infinite plane sheet, how it was? At any point it was at this, right? Like this, perpendicularly, correct? That's why I have made the lines like this. But if it was not an infinite plate, electric field lines will not be like this. Correct? So now that is the reason we have to take infinitely long plate. But in a room, how can you have an infinitely long plate? Not possible, right? For this straight electric field lines, for uniform electric field lines, for constant electric field, sigma upon 2 epsilon naught, remember? From infinitely large plane sheet, the electric field at any point near to that was sigma upon 2 epsilon naught, that was constant. How did it come constant? Because of infinitely long. But in a room, I cannot have infinitely long sheet. Right? So what we do, we keep this separation very small so that this sheet behaves as an infinitely long sheet. I'll tell you how. Why this is, so that sheet or the plate behaves as infinitely long. Clear? This is separate, okay? Fine. How it will behave as infinitely long? Suppose there is a very small ant, kitty. If that ant is here, for that ant this board will be infinitely big. Because it cannot see large distance, right? I can see, for me this board is very small. But if a very small ant is sitting over here, for that ant, this board is, wherever it will see, the board is going, right? For that ant, it is infinitely large board. The same way, if the separation is less. Now from here, if I take that ant and make it sit here, from here, if that ant will see, this sheet will look like infinitely long sheet. Correct? So if the separation is less, from any point between this separation, if I see this plate, it will look like infinitely long. I hope it's clear. Fine, that's why we keep this D comparable to A, it is very small. Okay. Now, so now notice area of both plates must be same. Shape may differ. Okay. Shape may differ. Suppose one is a rectangular plate, another can be a circular plate, not a problem. If the area is A for both, for both, this can happen. Okay. Because anyways the electric field lines will be like this. Next, distance between the plates must be very small. As I already told, D should be very, very less than A. So that here I'll write the plate behaves as infinitely long. Clear? I'll remove from here. I'll write this here and I'll explain this. I've explained this here. Fine. The more small the D is, the more will be the capacitance. We'll see now. Capacitance of a parallel plate capacitor. Now suppose this is a parallel plate capacitor. It is having some charge Q. So this will have a minus charge Q. Minus Q, correct? Area is A. Separation is D. Now, if I want to write electric field between these two plates, we have already done one question, right? Electric field between two plates, one is having positive charge, one is having negative charge, equal and opposite. We have already done. The answer was sigma upon epsilon naught, correct? See how at any point inside it, any random point, if I want to write electric field, it will be E1 plus E2. See how due to this sheet, at this point electric field will be in this direction. Let's say E1. Due to this sheet, at the same point electric field will be in this direction, correct? That is E2. And the value, that is why we are adding it. Negative charge towards negative it will be. From this up away from positive it will be, okay? So now if I add it, E1 is sigma upon 2 epsilon naught. What is sigma? What is sigma? Charge is given, area is given, charge per unit area, plus sigma upon 2 epsilon naught. So now for both the charges are same, the magnitude of charge is same, the area is same. That's why for both this sigma will be sigma only. It will not be sigma 1 or sigma 2. Okay. So now from here, sigma upon 2 epsilon naught, sigma upon 2 epsilon naught is sigma upon epsilon naught. This we already know. Between any two infinitely long plates having equal and opposite charges, the electric field will be sigma upon epsilon naught away from the positive charge and towards the negative charge. Fine. Now from here I can write this as Q upon A epsilon naught. Sigma I have written as charge per unit area. Okay. Now I need to write capacitance. Capacitance is equal to Q by delta V. This is capacitance, right? So now delta V is equal to minus E dot delta X, if you remember. Both were vectors, correct? But here E and this distance both are in same direction. From here to here, if I take delta X vector, it will be in this direction. Electric field is also in this direction. So it is 0 degrees, the angle between them. So if I do the dot product, cos 0 will be 1. So there is no need of this vector sign, correct? It will be E into delta X. Minus sign shows where the potential will be more, where the potential will be less. Okay, it is a scalar quantity. It is not representing the direction. So I can remove this minus sign also. I just want the value. For this capacitance, capacitance is also scalar. I just want the value, that's all. Okay, so from here, I can write it as E into D. Delta X is D here. So now E is sigma upon epsilon naught, that is Q upon A epsilon naught. Q upon A epsilon naught, and this is D. This is delta V. And C is equal to Q upon delta V. That is equal to Q upon Q D upon A epsilon naught. So A epsilon naught will go up, Q and Q will be cancelled. So this will be A epsilon naught by D. This is C. This is C. Again, very important. Very important. रात की 2 बजे भी ये फॉर्मूला याद होना चाहिए. Okay. Now see this formula. C is equal to A epsilon naught by D. Is it depending on charge? No. Is it depending on potential? No. It depends on the area. Epsilon naught, medium, or first I'll write D. separation between the plates. Epsilon naught, medium. Here it is air. Fine. This thing, these two plates are kept in air or vacuum. All right. Okay. Next. Find the capacitance of, these are very basic questions. We have to find the capacitance of this particular combination, we can say. Okay. So now C is equal to epsilon naught A by D. What is A here? A is equal to area of the plate. Area, this is length, this is breadth, L into B. Separation, D is given as D only. Correct? So this will be epsilon naught LB by D. This is the capacitance. Fine. This is the capacitance. Next, parallel plate capacitor is given. Shape can be any shape, right? So here a positive charge is there. Don't think that they are neutral. They are not neutral. Positive charge is there. It is written plus Q, right? Minus Q. The area of both should be same. Since it is given radius is R, so area is equal to pi R square. Separation is anyways given as D. C is equal to epsilon naught A by D. That is equal to epsilon naught pi R square by D. If you see, capacitance is pi R square by D. So now whether you give charge or not, the moment this plate was manufactured, the capacitance was decided. Correct? All right, next. Force on one plate of capacitor due to other plate. So now obviously this is positive charge, this is negative charge. So this plate will try to attract it. This plate will try to attract it. Correct? There will be an electrostatic force. How much is that force? Let's find out. Force will be equal and opposite. We know that if 2-point charges are kept, force is equal and opposite. The same way here also, force will be equal and opposite. So if we take out force on any one plate, the same force is experienced by the other plate. Only the direction is different. Okay. So let's find the force on this plate due to this plate. So on this plate, let's take any one point. See, electric field is uniform. So each and every point will experience the same force. This is electric field. Okay. So now I am taking any point. If any point here I take, the force experienced at this particular point, let's say F. What is F? F is equal to Q into E. Q here is Q, capital Q. That is Q into E. This is the force experienced by the entire plate. Okay. That is equal to Q into, how much is E? Electric field due to this plate. It is not sigma by epsilon naught. Due to one plate I am asking, sigma upon 2 epsilon naught. Correct? Sigma upon 2 epsilon naught. That is equal to Q. Sigma is Q by A. This is Q square upon 2 epsilon naught A. This is the force. This is the force. If you want to write the vector, for this plate it is in this direction, for this plate it is in this direction. Alright. Q square upon 2 epsilon naught A. Force on each plate of the capacitor. Alright. Next. Energy is stored in a parallel plate capacitor. Now again we have to find the energy. I hope now you know how to find the energy, right? See here, two plates are there. Right now they are not charged. This is the final diagram what I have shown. Right now they are not charged, both are neutral. So if both are neutral, initially the energy will be 0. Then now I have to store energy in them. For storing the energy I have to do some work. The same work will be converted into potential energy and it will be stored, correct? Now, they both are neutral. I have to charge them. For charging, first I'll give some energy to this. One dq charge will come out. That dq, if I put on this particular plate, it will come easily because this is neutral, right? It will come easily. Now this plate is having dq charge. This plate is having minus dq charge, correct? Now if I want to take one more dq from this, will it be easy or hard? It will be difficult. This is already negatively charged. I am trying to take out the positive charge from that. Negative charge will keep on attracting the positive charge. It will hold it like anything. I am trying to extract it from there. It will take more work has to be done, right? So now let's say I have done some work. I took out one more dq, and now that dq I am putting here. Now for putting this dq here, also more work has to be done, because now this is positively charged. This dq will repel this dq, which was already there, right? Now, so now work will be more than the previous work. Again, if I take one dq, for extracting this dq, again I have to do more work, because now it is minus 2 dq, it is plus 2 dq. Already minus 2 dq are there. I am trying to get one more dq from here. Okay, if I transfer it here, I have to do more work, because already it is plus 2 dq. It will repel more. So every time the work is increasing. Work is not constant, work is variable. In bringing each and every dq, for every dq there is a small dw work, which is variable. So what we'll do? We'll integrate it, correct? Energy stored. First we'll find the work done by external agent in charging these plates. Work done by external agent in charging these plates. That is equal to, last session I told you delta V is equal to dw by dq, correct? Delta V is equal to dw by dq. How it came, I told you. I had put a star also to make you remember this, correct? Now, before integrating, let's see what will happen finally. Finally, what will happen? This plate will have a plus q charge, this plate will have a minus q charge. Initially, they both were 0, 0. Some dq I have brought here. Okay, let me just show. And in bringing each dq, there was a small dw work done. Okay. Now, at t is equal to 0, how much was the charge on each plate? 0. See, overall if you see, the charge is 0 only. Plus q minus q. After t is equal to infinity also, if I make this as one system, the charge is plus q minus q, 0 only, right? But we don't see that way. We only see the charge on one plate. Okay, and we write that only. Okay, so then voltage, potential, 0. No charge, no potential difference. Capacitance, it will be C only. Capacitance is decided once the plate is manufactured. Fine. Because the separation is already decided, the area is already decided, where they are kept, the medium is already decided. Fine. Okay. At t is equal to some time t. Some dq I have brought here. So dq, adding on the dq at some time t, let's say there is a charge q here, minus q here. Okay, so at t is equal to t, q is equal to small q. There will be some potential difference. There will be some potential difference, delta V. Okay, let's say this potential difference is V. Okay, capacitance will again be C. At t is equal to infinity, when this is fully charged, okay, q is equal to q, delta V is equal to V, delta V, and C will be C. Okay. Now here, potential difference is equal to work done per unit charge, if you remember. So the small work is done in bringing the small charge every time. Delta V is equal to dw by dq. So now here, dw is equal to delta V into dq. What is the value of delta V? What is the value of delta V? anytime if you see delta V will be Q by C. At this point also delta V is equal to Q by C. Correct? At this point it is, let's say, small delta V. Correct? This is at time t. At time t. Okay? So delta V is Q by C. Whether the charge is this or the charge is this will change accordingly, right? This is small delta V at time t, this is at time infinity. Correct? So this delta V I can write as Q by C. At time t the charge was small q, capacitance was same every time. So this I can write dW is equal to Q by C dQ, integrating from 0 to W, and this from 0 to capital Q. From here W external, this is work done by external agent we are finding out, that is equal to 1 by C, which is constant, Q is Q square by 2. From 0 to Q, that is equal to Q square by 2C. This is W external. So work done in charging the plates is Q square by 2C, work done by external agent, and we know that delta U is equal to work done by external agent. So U final minus U initial is equal to work done by external agent. Are yes or no? From here U final minus U initial is 0. Initially the charge was 0. If in the configuration the charge is 0, the potential energy is 0. So U final is equal to work done external is Q square by 2C. So that means U is equal to Q square by 2C. This is the potential energy of the capacitor. In the last session also, the formula for potential energy was same. This only, correct? I told it is for all the capacitors. According to the capacitor, whether it is spherical or parallel plate, the value of the C will change. 4 pi epsilon naught R in case of spherical, then epsilon naught A by D in case of parallel plate. Okay. Next. In terms of capacitance and charge, again this also is the repeated slide, you already know. U is equal to Q square by 2C, just now we have found out. In terms of capacitance and potential, so that means I have to remove this Q. So if I substitute Q is equal to CV, Q is equal to CV, if I substitute it will be C square V square by 2C, C cancelled, half CV square. This is the answer. Fine. In terms of charge and potential means this C I have to substitute. This C if I substitute by C is equal to Q by V, correct? If I substitute this as Q by V, this will be half Q by V, V square, V cancel, half QV. That is the formula, see. Half QV. Alright, so this is the formula for energy. All formulas are same, the value will be same, right? You have just substituted and got. This is in terms of capacitance and charge. This is the same in terms of capacitance and potential. This is in terms of charge and potential. Alright. Next. Heat generated. Okay. Understand one thing. Suppose there are two plates. Fine. A battery is connected to it. Now, okay, I forgot to tell you one more thing. Initially, I told parallel plate capacitor. The very first slide. This is a parallel plate capacitor. It becomes, when this becomes positive, then this becomes negative, equal and opposite charges. But how does this happen? There are two ways. One way, these two plates connected with a battery. Connected with a battery. Once we connect it with a battery, what happens? Two capacitor plates are there. I have connected with a battery. This plate is connected with positive terminal. This plate is connected with negative terminal. So that means, let's say this plate will be positive, this plate will be negative, correct? We can assume that positive charge is flowing and going on this plate. Negative charge is flowing and going on this plate. This is how this particular thing, this particular configuration comes. All right. So this is providing electrical charge. This is providing energy. Battery does not provide electrons. It only moves the electrons. Battery does not provide charge. It will move the charge. So what it basically did is it took electrons from here and gave it here. Electrons from here gave it here. Electrons from here gave it here. So this plate became positively charged. This plate became negatively charged. Clear? It is very simple now. Current flows like this. Electrons are flowing opposite direction of current. That means electrons are flowing in this direction. Where are these electrons coming from? From this conductor plate. Conductor plate is the notion of electrons. Electrons are flowing from this plate to that plate, this plate to that plate. Clear? Okay. Second way. Keep a plate here. Keep one more plate here. Earth this plate. And this plate give positive charge to this plate. What will happen? When a positively charged plate will be in front of a negatively charged plate, in front of a neutral plate, negative charge will be induced here, correct? But since it is grounded, the excess positive charge will go to the earth. So this will be a permanent configuration like this, okay? I hope you got this. All right. Now let's go from where we came. So now this is the battery. This battery is actually charging this capacitor. Battery is giving charge to this capacitor. That means battery is providing energy to this capacitor. Okay. If I ask you energy supplied by battery, energy supplied by battery, that is equal to work done by the battery. How much is the work done by the battery? If suppose this plate finally has got plus Q charge and the potential difference is V, how much is the work done by the battery? Q into V. That means Q charge has been flown through the battery, correct? Through this, Q charge has been flown and potential difference is V. So how much work is done by the battery? Q into V. Right? Now, this Q, if I write it as CV, can I write? If I want to write it in terms of capacitance, I can write this Q as CV. Q is equal to CV. So from here, I'll write in bracket. This will be CV into V, since Q is equal to CV. What is this? CV square. That means energy supplied by battery is CV square. So the energy stored in this capacitor should be CV square. The energy is coming out from here, going here, coming out from here, going here. But the energy in this capacitor, just now we found out how much it is. Half CV square. In terms of capacitance and potential, it is half CV square. Energy supplied by battery is CV square and energy stored in the capacitor is energy, there I'll write, energy stored in the capacitor is equal to half CV square. So where is the half energy gone? From here CV square is coming, capacitor is taking half CV square. Where is the remaining half CV square? Heat. This energy gets converted in form of heat in the circuit. The circuit will get some heat, no? Heating effect of electric current, correct? That heat will be half CV square. I hope you got it. So heat is equal to energy stored in the capacitor minus energy supplied by battery. UC minus UB I am writing. That is, energy supplied by battery minus energy stored in capacitor. That is equal to CV square minus half CV square. That is equal to half CV square. Okay. So how much ever energy the capacitor is having, the same amount of heat also the circuit is taking. Okay. The same amount of heat is there in the circuit. Clear? Note it down. Heat is equal to half CV square. Or this formula is important. Energy supplied by battery minus energy stored in the capacitor. Next, let's see a question. Two parallel plate capacitors are pulled apart from separation D to 3D. What is the work done by external agent? So two parallel plates were there, they are kept at separation D. Then by external agent it has been moved to separation 3D. How much is work done by external agent? There are two ways of doing this question. One way, by the energy, work done is equal to change in energy, correct? Work done by external agent is equal to delta U, that is U final minus U initial. If I find this, I'll get the work done by external agent, correct? Let's do this. So that this is equal to, we'll go in the next. So work done by external agent is equal to U final minus U initial that is equal to, for this configuration, what will be the energy? Half Q square by 2C minus, for this again Q square by 2C. Here the C will be different, let's say C dash. Why C will be different? Because the separation increased. For here if I want to write C, C will be epsilon naught A by D. For here if I want to write C dash, it will be epsilon naught A by 3D, correct? Epsilon naught A by D, epsilon naught A by 3D. Area is still same, only the separation is increased. So here Q square by 2 epsilon naught A by 3D minus Q square by 2C epsilon naught A by D. 3D, 3Q square D by 2 epsilon naught A minus Q square D by 2 epsilon naught A. From here, 2 epsilon naught A is anyway same. 3Q square D minus Q square D, 2Q square D. 2Q square D by 2 epsilon naught A, 2 cancelled, Q square D by epsilon naught A. This is work done by external agent. Q square D by epsilon naught A. Clear? Easy? There is another way. Method 2. Okay. Method 2. Work done by external agent is equal to force into displacement, correct? Direction of force and displacement is same. So now basically the force on this, let's say this I have fixed, I am moving this one. To take this away, I have to put force opposite to the electrostatic force. Because of this, the force on this is in this direction, correct? So now keeping this fixed, I want to take it away. Since this force is there, the same amount of force, if I apply F external, this is electrostatic. Electric force I'll write, okay? F electric force, this is inside, F external is outside. I have to put an opposite, equal and opposite force. If I put just more than that, it will shift, correct? F external, the value of F external will be, value of F external will be Q square by 2A epsilon naught. What was the force? Just now we took out. Q square by 2 epsilon naught A, correct? The same I have written. Q square by 2A epsilon naught into D. How much is D? D is the separation. How much? Earlier it was D, then it became 3D. So how much distance this force has shifted it? 3D minus D. It was already at D. Then this force has shifted this to 2D more. Right? So 3D minus D is 2D. That is Q square by 2A epsilon naught 2D, that is equal to Q square by Q square D by A epsilon naught or epsilon naught A. Properly I'll write, okay? Q square D by A epsilon naught. This is work done by external agent. Okay. If they would have asked work done by electrostatic force, a minus sign would be there. Fine. This is F external. We have gone in F external direction only. That's why it is positive. F dot D dot product, if you want to see, both D and force were in same direction. Cos 0 is 1. That's why I have directly done F external into D. Clear? D, okay, D you will get confused. Delta X. Okay. See, both the answers are same. Both the answers are same. So whether you do by energy or you take it out by work is equal to force into displacement, both are same. The answer will be same. Next. Charge distribution on each plate when unequal charges are given to each plate. So now initially there are unequal charges. Till now what we were seeing, there were no charges, then the charge distribution happened because of battery. Fine. Now there are unequal charges initially. So how will the charge be distributed so that it becomes capacitor? Because capacitor inside, in the inner surface, equal and opposite charge should be there. Now let's say some charge flows from here to here. What will happen if I put a battery or anything? What will happen? The charge will start flowing from here to here, right? Or let's say finally, because of charge distribution, I am not connected to the battery. I have kept these two plates like this. Q1 charge is here, Q2 charge is here. How much charge how the charge will be distributed? Let's say here it became Q1 minus, or inside this a charge Q has come. Okay. So outside the charge will be Q1 minus Q. Are yes or no? Total charge has to be Q1. Charge, let's say inside came as Q, outside Q1 minus Q. Here inside, let's say some charge X has come. Outside it will be Q2 minus X. Total should be Q2, correct? Okay. Now, if I want to write electric field, before that, before writing the electric field, in which point, for which point do I have to write electric field? For this particular sheet, if I take any point inside the thickness of the sheet, for this sheet, if I take any point inside the thickness of the sheet, okay, let's say this is point A. And here for this sheet, I have taken any point B inside the thickness of the sheet, okay. For A point, if I want to write electric field, since it is a conducting plate, electric field at A will be 0. Correct? Electric field at A will be 0. If I write the electric field at A, due to all the charges present, the sum should be 0. Let's write. First we will write due to this particular charge. Okay? This is on this side of the plate. Right now this charge, if I take this side of the plate, this charge is somewhere here. This will be the thickness of the plate. This point, sorry, not charge, point. This point A is inside. This is the outer surface, this is the inner surface. For this capacitor also, let's say this side is the inner surface, this side is the outer surface. B point is somewhere between somewhere in the thickness. Okay. This surface is having charge Q1 minus Q. This surface is having charge Q. So for this A, electric field due to this charge, it is like an infinitely long sheet having charge Q1 minus Q. Can I write electric field as sigma upon 2 epsilon naught? Sigma is Q upon A, right? Q1 minus Q upon A epsilon naught. Correct? Fine. Due to this charge, can I write? So initially, what I am assuming that all the charges are positive. Whatever will be the charge, whether it is negative, positive, it will come finally. Okay. So if I consider all the charges as positive, due to this charge, the electric field will be in this direction. Due to this charge, the electric field will be in this direction. Due to this X, the electric field will be in this direction, opposite. Due to this Q2 minus X also, the electric field will be in this direction, opposite, correct? Away from the charge. So now this This one is due to this, that is Q1 minus Q upon A epsilon naught. Now this one if I write due to Q, so that will be minus Q upon A epsilon naught. Why minus Q? Opposite direction. Only this will be positive. Rest everything will be negative because it is opposite. Okay. Due to this charge, if I want to write at A, minus X upon A epsilon naught. Charge per unit area and in the denominator epsilon naught. Due to this charge, Q2 minus X. If I want to write electric field here, it will be again in this direction. That is minus Q2 minus X divided by A epsilon naught. Correct? Now, this EA is equal to 0. Q1 minus Q upon A epsilon naught minus Q upon A epsilon naught minus X upon A epsilon naught minus Q2 minus X upon A epsilon naught. A epsilon naught is common. So if I write it like this, this minus, if I open this, it will be Q2 plus X, correct? This will be same upon A epsilon naught. This minus I have taken inside, minus Q2 plus X. That's what I have written. Now see here, this X and this X will be cancelled. This will go to the other side, multiply, it will be 0. What did I get? 2Q is equal to, or let me just write the equation initially. Q1 minus 2Q minus Q2 is equal to 0. Minus minus plus, so this is 2Q2. From here, Q is equal to Q1 minus Q2 by 2. This is Q. Fine. The same opposite charge will come here. Let's see. For X, for this point, if I want to write for B, due to this Q1 minus A, due to this first, let's write. This is a positive charge, so electric field will be in this direction. This point is this side. It will be away. From this charge, the point is this side, away from the charge. This is due to X. From this charge Q, again it will be away. From this charge Q1 minus X, again it will be away. Correct? So now, for X I am writing E at B. I am writing E at B, that is Q2 minus X upon A epsilon naught minus, okay, due to this charge. Now this time I am taking this direction as positive. Now that is up to you. Okay, anyways, since is equal to is 0, so it doesn't matter. Okay, due to this X upon A epsilon naught minus due to this Q upon A epsilon naught minus due to this Q1 minus Q1 minus Q upon A epsilon. This will be 0 EB again, because inside the conductor, inside the thickness I am talking about, electric field is 0. That is again Q2 minus X minus X minus Q minus Q1 plus Q. This minus I am taking inside. In the denominator, it will be A epsilon naught. Q and Q is cancelled. Some similar kind of expression is coming. See, this A epsilon naught will go here, multiply 0. Q2 minus 2X minus Q1 is equal to 0. X, if I take other side, X is equal to Q2 minus Q1 by 2. Q2 minus Q1 by 2. Can I write this as minus Q1 minus Q2 by 2? If I take this minus sign out, can I write it like this? Sorry. Can I write it like this? Minus Q1 minus Q2 by 2. It was Q2 minus Q1 by 2. This is what it is written. Q2 minus Q1 by 2. Correct? See, this is q1 minus q2 by 2. This is minus of q1 minus q2 by 2. Equal and opposite charge came at the inner surface, q and x. Okay. Q is here. Q is q1 minus q2 by 2. X is minus of q1 minus q2 by 2. These are two plates. Outside, how much charge is there? Q1 minus Q. So Q1 minus Q, Q1 minus Q is Q1 minus Q2 by 2. Minus, if I take inside, 2 if I multiply here, this will be like this. 2Q1 minus Q1, Q1 plus Q2 by 2. Correct? So this will be Q1 plus Q2 by 2. Okay? This is Q1 minus Q. Another was Q2 minus X. Q2 minus X is equal to Q2 minus of Q1 minus Q2 by 2. Minus minus will become plus 2Q2 plus Q1 minus Q2 by 2. That is, Q2 will be minus Q1 plus Q2 by 2. Q1 plus Q2 by 2. So here Q1 plus Q2 by 2. I hope you got this. So whenever unequal charges are given, see here what happened inside, the difference of the charges by 2. Q1 minus Q2 by 2. This is also Q1 minus Q2 by 2 with a negative sign because the charges should be equal and opposite. And outside, if you see, the sum of the charges divide by 2. The sum of the charges divide by 2. Both. So outside it will be same. Inside equal and opposite. Okay. Like this it will be distributed. Let's do a question, you'll understand. How will the charge be distributed on each plate? Initially, this kind of configuration we have given. This charge is there. Okay. We know inside how much charge will come? Difference by 2. Difference by 2 means 20 minus 6 by 2. 20 plus 6, 26 by 2. This will be 13 microcoulomb. So if this is 13 microcoulomb, this will be minus 13 microcoulomb. Correct? Outside, sum by 2. Sum by 2 means 20 plus minus 6 by 2, that is 14 by 2, that is 7 microcoulomb. Here also it will be 7 microcoulomb. Outside, in both the plates it is same. Now if you see the sum, 7 plus 13, 20, minus 13 plus 7, minus 6. Clear? Okay. Find the capacitance of the given system. So now we are given with two unequal charge plates. We are given with the area and D. They are telling to find the capacitance. Some people will try to derive it, but some people know capacitance does not depend on charge. Capacitance was decided once these plates were manufactured. Why? Because the area was decided then, the separation was decided then, the medium in which it is kept, it is decided then. So now capacitance is equal to epsilon naught A by D. If this is kept in air or vacuum, fine, this is the capacitance. It doesn't matter how much ever charge is there on the plates, this will be the capacitance. Or if you want to know, or if you want to get it from the charge only, let me show you. This is 2Q, this is Q, so inside how much will it be? Difference by 2. 2Q minus Q is Q by 2. This is Q by 2. Here it will be minus Q by 2. Outside 2Q plus Q, 3Q by 2. This will also be 3Q by 2. Correct? 3Q by 2. We are much bothered about the charge which is inside. We don't care about the charge which is at the outer surface, because this charge is only going to make the electric field. From where I'll get the potential difference, from where I'll get the capacitance. Okay. So electric field, if I want to write down, how much will it be? Sigma upon epsilon naught. Anywhere in between, any point. Sigma is charge upon area. Charge is Q by 2. Area is A, epsilon naught. Delta V is equal to E into D. That is equal to Q by 2 A epsilon naught into D. into D. Capacitance is equal to charge upon potential difference. That is, how much is charge? Charge is Q by 2 here. Charge is Q by 2 here. So Q by 2 divided by Q by 2 into D divided by A epsilon naught. Q by 2 got cancelled. How much we got? How much we got? Epsilon naught A by D. It will be same. Clear? I hope you got this. So if they give like this, don't get confused. Capacitance doesn't depend on charge. If area is D and given, you have to find this way. If area and D is not given, then there is a different thing. Then you have to stop somewhere here only. Fine? Or where the charge is there, potential difference is there. Okay? So I hope you understood today's session. You enjoyed today's session. You liked today's session. In the next session, we are going to study combination of capacitors. Again, very, very interesting and very important also. Question will definitely come from here in board. Okay. After this, we'll see. After this lecture, there will be one more lecture on combination of capacitors. That's why I've written one. That will be part 2, where more good questions we'll see, which will be from competition point of view. Okay. So if you like today's session, do press the like button, share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Okay? You can go visit our website www.v-learning.in, where the classes what we are providing here, you will be getting there. Along with that, you will be getting lecture notes also. You can download and study. Okay? We'll meet up in the next session. Till then, keep learning from V Learning. All the best.